Hi, I'm Rick Francisco, lab tech here for the physics department. We have a new instrument that we are going to be using for the spring semester. This one is called the Centripetal Force Apparatus. It has two sensors that will be detecting on your experiment that you're going to be doing here. The first one will be the dual range force, and then the second one will be a photo gate. And then you're also going to need a LabQuest 2, and then you're going to need Logger Pro on your PC to collect and analyze your data. And that should be it for right now. And the professors will give their information too. Thank you.
So since you have two sensors, the fourth sensor will appear measurement in there. But we have a second one that you can see if you click this uh, toolbar over here. And then you have your photo gate and you have measurements of your dual force sensor here. So the only setup you have to do on the photo gate is to tell which distance you are using. So set distance or length, and then you choose user defined. So the way it goes, if you can show this wheel over here. So this wheel has 10 spokes, and so it goes one turn, 360 degrees, 10 spokes. So it can give you the angle in between each one of these marks, and that angle over the time that it goes around gives you the omega, and is the same omega of your mass point. So we have to go over here and set that to 0.628, which is 2 pi r divided by 2 pi divided by 10. So 2 pi is the entire circle by 10 divisions. So you have 2 times 3.14, so 6.28 divided by 10, 0.28. And the units, it's not in meters, should be radians. Okay, then you're out of here. The next thing you do is to bring a built-in experiment given by the manufacturer of this centripetal force apparatus. And then what you do, you go to this open folder right here, click on it, and in experiments, look for sensors, probes and sensors right there. So click on that one, and then find your centripetal force apparatus. Click on that, and then you have five experiments you can do with it. We are doing the first one. Click that one. And then all these windows will disappear, and then you have a nice set of 3 windows, all nicely done. So the first column here is going to give you time. The second column is going to give force that comes from the force sensor. And this angular velocity here is the one calculated by the wheel. But the time between those two sensors are not the same. And then what this window does is to interpolate between the values of omega we have, and then you have a force column that is calculated directly from the sensor, and you have an interpolated one that is going to match the omegas that are calculated. What I like to do is also to create a new column here that I call calculated column, or calculated force. I call FC, and that is equal to the mass that is plugged in there, because the centripetal force is mv squared over r, or m omega squared times r. So the mass we have here is 50 grams of this black supporter, plus whatever mass in metals we have here. So we have 250 250 plus 50, about 300. So I'm gonna mark 300 grams in there.
In kilograms, right?
Yeah, 0.300 kilograms times omega square. So we have a column of angular velocity square right there, times the distance. So the distance is the one that you are going to set your point mass. And then I will pass it over to Mike now. Mike is going to set everything as if he were a student. And then he's going to give me the radius.
Okay, so first off, this mass here is 6 grams, you say?
This mass has a weight of 0.6 newtons, which we need to zero.
We need to zero
when we
that.
start the experiment.
Okay, so a couple things to note that were sort of glossed over. This dual range force sensor, the string has to come across this way, across this pulley here, and then straight down to this pulley. Now, this string here should not be off center like this. It has to be in the groove, otherwise you're going to get some really weird results from the system. The other thing to note is there are, let's see, 2 sensors here, like Celso and Rick said, that there's this rotating system here with the spokes. And we have the dual range force sensor here measuring the force coming as this is rotating. This is going to be flung outwards like this. Now, as it moves outwards, again, from Newton's first law, because it wants to try to move in a straight line, the string is the only thing holding it in place in a circular pattern, or a circular path. And so this is the force that prevents it from moving off in a straight line. In other words, this is the centripetal force. There's a couple of ways to approach the data collection for this. I don't know if you can see this back here. The formula looks like this for centripetal force. And since we have omega, this can translate into the v squared here, the linear speed counterpart. And so as this is being rotated around, as we see here, the mass moves outwards like this, and it provides a force on the string. And this is going to be translated this way, and eventually down to the force sensor. So this is going to be measuring the force as this is rotating around and around like this. And meanwhile, the sensor here is measuring omega, all right, the angular speed as this thing is rotating around. Now, the way Celso set this up over there, we have an omega squared column, which is automatically calculated, which is the counterpart for the v squared here. And we also have, what else do we have? The force
From the sensor.
The force from the sensor over here. And we also have the interpolated force. Now there's also another column you could put in automatically if you wanted to, is the percent error between the this force and the other one to see how much it sort of like wavers from the 2 values there. And so one way to take the version to take data here is by applying this formula here and taking a look at the 2 graphs here. The top one is force versus time. The bottom one is omega versus time, the angular speed versus time. And if we go ahead and run the data there, let's see if we can just do this.
Wait, I need the distance.
Oh, the distance.
Yeah.
The distance here is 12 centimeters from the axis here.
If you unlock, you can show them how they change the distance.
Oh, okay. So we can change the distance by moving the force sensor freely like this. And then we can move this outwards over here. As you notice, this is all one thing over here. So let's say we move this over to 15 centimeters, right, just for this. And then there's no screws here because this has to freely move. So once this hits 15 over here,
So I'm going to write 15 here in my equation.
yeah, and you want to clamp this down over here by turning this screw. And so this thing will fly out as much as 15 centimeters. And of course on this side you have to counterbalance this by putting the counterbalance mass at 15 centimeters, otherwise it's going to wobble around erratically. You don't want that to happen. So They're both at 15 centimeters or 0.15 meters away from the axis here of rotation. The setting on here for the dual range force sensor is set at plus or minus 10 newtons, and I believe that's where we want to set this thing for this experiment.
So I'm creating another column with errors.
That's going to show up on there as an additional vertical column there for errors.
Errors.
Okay, and the easiest way to collect data on here so that it avoids a bunch of jumble on the graphs there is to spin this up. Okay, and then hit the collect button at the top there as you do with Logger Pro. And so what I'm going to do is start rotating this, and obviously before you do this, make sure that everything is nice and level. All right, because if these legs are not level, then this thing's going to be wobbling quite a bit. So it's spun up now, and as you can see on the graphs over there, as this thing starts to slow down, we see the first graph up top there, the angular velocity is slowly spinning down. All right, so there is a definite deceleration or alpha going on here that you can calculate as well if you wanted to. But at the same time, we notice that the force is decreasing, which is the second graph that you see there. Okay. And they have a pretty good correlation between the two. The percent error that you see so far between the two forces is pretty close to what?
It's 10%, so it's not good.
Oh,
I wonder if, I think we forgot to zero.
yeah, we forgot to zero it.
Yeah,
So can you go through the steps on how to zero that?
let's do it again. So
Okay.
let's stop that thing.
So Celso, go ahead and demonstrate how to zero.
So now we have a 0.1 Newton error.
Yeah, there's nothing on here right now, so there
So,
shouldn't be anything.
Yeah, experiment, go to experiment, the toolbar experiment and 0. And now the weight is gone as far as sensing is concerned. So let's try to do it. And we have 15 centimeters distance, right?
Yes.
Yeah, okay.
All good? All right, so start spinning it up again. And I'm going to let go. This should give us some nice clean data here.
Now
Again,
we
the
have
top one is angular
0%.
velocity. So you're getting 0%? Or pretty
Yeah,
close to it.
2%. Yeah.
Okay. So as you can see, the two graphs there are nice and clean at this point. There's not no wobbling, no jitters or anything of that sort. As it starts to slow down, the force also on the string is expected to be decreasing as well, which is exactly what we see there. Right.
I'm gonna do one graphic of
Okay.
your, in fact, we don't need it, the graphic of forces was calculated by the omega square that you mentioned. That would be a nice thing to do.
Yeah, and so V is equal to R omega or omega R. So this thing basically translates to F is equal to M omega squared times R, right? So this formula here indicates that M and R, if you plot force versus omega squared, the slope should be equal to mass times the radius of the axis of the string here, all right, which you said was 15 centimeters in this example.
So we take a slope there, 0.045.
So we got slope is equal to 0.045.
And we have a mass of
So 300 grams?
300 grams.
So 0.3 kilograms.
And a distance of 15 centimeters.
So it works out.
It should.
Yeah, it should work out. Okay. All right. So yeah, so you compare the slope here to your value of m multiplied by r by itself, and see how close those two values are. That's one way to confirm that this is, that this is valid, that the formula for centripetal force is valid. Again, this apparatus is replacing the older one for Physics 2A and 4A, where we had a setup where you have to spin it by hand, and you had a spring basically holding the mass inwards, and you're basically trying to rotate it so that the spring stretches out to a certain point. And then replacing the spring with a hanging mast to leave the spring on there, and then having a secondary force on the outside to pull it out so that it reaches the same position again, and then comparing those two values. In this case here, we don't have mg, we don't have a hanging mast that we put onto the system anymore. What we're doing is we're comparing the force associated with the rotation, which is going to be mv squared r, or mr omega squared, this one down here, and comparing it to the measured force of the system that is measured using the sensor over here. And if you do this, and if you're clever enough, like Celso over here, putting the percent error onto the system, then you'll be able to read off what the percent differences are, or percent errors are, very quickly. And you can see that they are within the 10% mark. In fact, they're pretty close to 0% for this experiment. Anything else we need to add to this?
Is when we are going to use this apparatus. We thought it's a big of a work to get 15 of those in the classroom, so we would like those to be used by 2A, 4A in the same week, or 2 weeks if we decide to extend in 2 weeks. But so somehow we have to agree with that, and this probably should be out after we teach Newton's law. Mm-hmm. So we should be in sync, academically with our course outline or course content, so that by the same week we can have the students working on that apparatus.
The reason why we are trying to enforce this semester is because of the logistics of having to set each of these things up. There's 15 of these setups. It would be kind of troublesome for Rick to have these set up 1 week and then tear them down, and then have another professor, a few weeks later say, hey, we got to do the lab now, and have to set up everything all over again. So it'd be nice to have it all done within 1 week framework, so that Rick and the equipment doesn't get all cluttered at that time. So I don't know when we typically run this.
We should send to Ben and Rick our lab intent this week, so we could, ideally we should try to match labs, in the same schedule as much as possible. So please send your labs to Rick and Ben this week before class starts. And I guess that's it.
All right, thank you.
All right, thank you.